normally, in pretty much all my classes, what I'm thinking about when I do this is, what sorts of questions would I find interesting to ask on an exam, right? So I'll go through the homework and flip through the book, and I'll just look through all the stuff that you guys have done and say, oh, that's a cool question, or that's one. If anything, these things, and there's too much on here. I can't possibly write you an exam that has like 16 questions on it. But it sort of gives a coverage of the topics that I want you to know and the idea of the computations. So normally the deal I try to make is that if you can work your way through the, I mean, it's not necessarily going to be like, oh, you're going to sail through with a 100%, but if you can do everything on here, you're going to get probably at least a B on the test. I don't write trick questions. I'm not going to introduce ideas I didn't put on here. There might be things that are related to these ideas, and they're almost never going to be literal copies of the questions, but the ideas that are covered here are the same ideas that you should expect to see. So it'll be some subset of things that look like this. Are there any other questions I can answer about it before I open the floor up to questions, like sort of content questions? Anything about the exam itself or the administration of the exam? Yep. These will be posted solutions. Yeah, I haven't had a chance to write these up yet, but tomorrow I don't teach on Fridays, which means I have an opportunity tonight to go through and actually write these up. They'll probably be on by hand, and it'll either be in the OneNote or I'll post it up into the exam one module, but it'll all be there. Now, because I do this in one go, you can imagine if I'm going to solve 20 math problems, there's a chance that I'll make tiny mistakes in the sheet. So just because you get something different than me, don't decide that your entire basis for reality is wrong, right? That sometimes I make small mistakes, and reach out and ask, hey, is this computed correctly?
6C.
Forget 6C. Forget it.
Is there even supposed to be like a D squared D0 on the right side of that?
Yes, actually. So basically, the deal is, if you did question 31, which was the question about polar coordinate, the change of polar expressing the differential operators in polar coordinates. This is the same question, but you just take that formula for d2 dx squared and dy dx squared, and you just add the d by dz on both sides. And that's it. I mean, it's literally the same thing, right? It's the formula that you did. And if you did 31, this question is dead easy. If you didn't do 31, and you wouldn't have after I told you not to worry about 31 because it's insane, it doesn't really reveal anything interesting. The point of this question mostly was, you might ask, okay, what was the point? I thought this was going to be a baby computation. I wrote this back when I hadn't looked at how bad 31 actually was. And the idea here is really what we're trying to talk about. We haven't talked about coordinate systems in here yet. And I'm trying to remind you that there's these three-dimensional coordinate systems. So we'll see them later in the class probably. But it was just a reminder like, oh, hey, by the way, cylindrical coordinates exist where you can just take polar coordinates and then stick a height on it. Right, that's it. You just take polar coordinates and then let Z like tell you the height over your polar coordinate of space. It's sort of they're beautiful coordinates, but they're kind of cheesy, right? They don't, in a lot of applications, they don't work because you choose the coordinate system based on the system that you're studying. So if things move in straight lines, you use Euclidean coordinates. If things move in 3 dimensions and arcs, usually you work in spheres because things are traveling in 3-dimensional space and curving arcs. But if you happen to have a system with some sort of crazy symmetry in it, then why not use the beautiful symmetrical cylindrical coordinates, right? So like I said, I put this question on here before I realized that I was just going to throw 31 in the game. Anyway, so yes, I'm happy to talk about 6C, but let's talk about it at a different time. Okay. Unless you guys really want to see me do algebra on the board for 20 minutes. Yep.
I was just also the calculators, yes or no?
Okay.
Calculators, how simplified.
So that's a good question. So no calculators, but you won't need them because I'm not going to ask you to simplify anything. So the rule in my classes that like these computational classes is you're responsible for calculus. You are responsible for no algebra. Right? I'm not testing algebra. If you plug something in, you get I say, oh, compute some tangent plane. And you have this ridiculous expression with fractions all over the place, just leave it alone, right? It's actually easier for me to read what you did from the unsimplified expression than the insane math that you cook up to boil it down. I've got to figure out where the mistake was in some noodle pile of arithmetic. Like, I don't care about your arithmetic really, right? So that's part of the deal about no calculators is I ask for no simplifications. I'm also not going to be doing numerical approximations either because that would require having you guys have calculators. So yeah. Now I know what the follow-up question to that is what formulas will you be providing on the exam? So if somebody was going to ask that, I'll just preempt the question and tell you. So my inclination is that nothing I asked you to do here requires a hardcore formula, right? I mean, like when you went through this sheet, what you should have noticed is we stuck to the basics. Basically, if you know how to compute a derivative, which you should be able to do without a formula sheet, and you know how to compute a tangent plane, which you should be able, or a linear approximation, which you should know how to do without a formula sheet, because there's one formula. Literally the only formula is a linear approximation for a function is given by the value of the function of the vector plus the derivative of the function of the vector times x minus a. And that's all you need to know, right? That's the hardest equation that we got, is this one. Actually, let's see if people actually know this. What's the gradient? What's the gradient of f equal to? Fx, fy. I guess I have to tell you the number of variables we're dealing with, right?
Yes.
How about f takes some interval in R3 into R? What's the gradient? Fx, fy, f, z. Right? It's just it's a vector of partial derivative. That's the gradient. What other formulas do I see in here? There's the gradient, there's df. Okay, suppose f looks like this. F of x, y, and z is equal to f1 of x, y, and z, 2 of x, y, and z. So this is a function f that takes R3 and spits out things in R2. What's df? Perfect. You can think about the first row here as being the gradient f1 and the second row as being the gradient f2, or if you like, it's the first row's derivatives of f1. So the derivative with respect to x of f1, the derivative with respect to y of f1, the derivative with respect to z of f1. Each row corresponds to one slot of the function, the same slot that the function spit out into, right? First row of the matrix, same as the first row of the vector. Dx f2, dy f2, dz f2. Am I going to ask you to compute anything from the definition of the derivative? No. The second derivative for vector valued functions, or the second derivative? Okay, so you have to be really careful about what you mean by second derivative here, right? So you can talk about second derivative, like the components of the second derivative, but actually this matrix and its second derivative is very hard to write down, right? There's a whole other like formalism that's used to write down second derivatives that involves a matrix called the Hessian matrix, which we're going to get to, or there's a Jacobian matrix, which is this, and then there's a Hessian matrix, which sorts out where the second partial derivatives live. And so in some sense, the Hessian is going to be the second derivative, but we haven't talked about it yet because it arises naturally in the study of Taylor series. So we're going to talk about matrix second derivatives when we talk about Taylor series. Yeah. It's like the matrix of all the mixed partial derivatives of a function, but it only applies to a scalar valued function. And for those of you that want to go past that, there's this wonderful world of insane objects called tensors. If you've never heard the word tensor before, one way of thinking about a tensor is, what if you have too many dimensions to write down? I mean, if I have a function here, you can imagine, I guess I don't want to get crazy with this. The more derivatives you take, the more dimensions you need to organize all the possible mixed partials. And so instead of having a line of numbers or a square of numbers, the third derivatives are organized into a cube. The fourth derivatives are organized into a hypercube. And there's a general study of things called tensors that show up all over, for example, physics and higher physics, where your whole life is tensors. Okay, so I didn't know what a tensor was until I got to grad school. So like anybody who wants to see how derivatives work in higher order in like as an extension for this class, I'd be happy to talk about it outside of the class. How do I compute the chain rule? So if I just say, oh, I've got some function f composed with x, and I want to compute its derivative. df dx. There, now it's in its most general form. Right? Chain rule is easy because you just multiply the derivatives of the functions you're composing. How do I, okay, what does this symbol mean? The directional derivative of f of a in the direction u. How do I compute it? U dotted with the gradient. Oh man, that's terrible. So this one is one I absolutely recommend that you know, because you can compute this from the limit definition if you really want to, but presume that the functions you're dealing with, I'm going to give you functions that are nicely behaved, and that you should know that the way you get a directional derivative is you dot against the gradient. So the gradient does, right? When is the directional derivative maximized? Same direction as, well, no, when u points the same direction as the gradient vector. Why? But why?
Cosine 0.
Yeah, because there's this cosine running around inside here, right? A dot product has really secretly got a cosine running around inside of it, because of the definition that says that this is the length of u times the length of the gradient of f in the direction a times the cosine of theta, but the length of u is always 1, because we always assume these are unit vectors. And so why is this maximized? Well, for what value of theta is this maximized? When theta is equal to 0, which means it's literally parallel to the gradient vector. Yep.
So that was the maximum.
This is the maximum happens when they point in the same direction, and the minimum happens when they point in opposite directions. What if they're perpendicular to each other? How much change is there? What does that mean about the behavior of level curves and gradients? There's a level curve for a function. What is a level curve? If I say level curve, what do I mean? After all, question 2b says draw several level curves. How are you going to draw a level curve? You don't know what one is. What's the level curve? C, well, I mean, it is equal to something. What's it equal to? Yeah, you basically set the outputs, right? Your sort of z values. You set the z equal to c, and you figure out the equation f of x y is equal to c. What do I know about the gradient and level curves? They're perpendicular. And that actually is, that's a result of this, right? When theta is equal to pi over 2, God help us all if anybody in here tries to work in degrees. No such thing. We're not sailors. There's just radians. That's all there is. Units, all you scientists. Anyway, when these things, so basically what it says is when you're traveling perpendicular to the gradient, that means that there's no change in height, and that's actually why this is true, right? These are curves where the height doesn't change as you move along, and so that means the direction in which your height doesn't change, which is perpendicular to the gradient vector, must also be the tangent line to the level curves. It's kind of how it all fits together geometrically. What else do I want to say here? How do I show that a limit doesn't exist if I've got some crazy function? You guys can also ask me questions too. I'm just blathering until I see hands go up. Does anybody have any questions before I continue talking? I'd be happy to answer any. Yep.
You was talking about like when you take derivatives of scalar value functions and vector value ones, and then put them together, like ones in a row.
Okay, so how you actually glue everything together, you mean? So like if I had something like f of, let's say f of x, actually how many variables do you want f to have? Do you want f to be a scalar or vector value? All right, I'll tell you what. I'm just gonna give you some functions, right? How about f of x and y is equal to x, y? Right, there's about a simple function I could. How about I want to put this in polar coordinates? So I'm going to define a function r, which is equal to r cosine theta, r sine theta. Right? there's a polar coordinate transformation. And let's suppose, so I think what you're asking is, how do I compute the derivative of f if I compose it with r and actually put it all together again as one object, right? So this says, what is the derivative of f if I do this coordinate change in the polar coordinates? Okay, so the derivative of f with respect to its original variables times the derivative of x with respect to its variables. Right, so I'm not going to plug anything into f. I'm just going to compute its matrix of derivatives. R. This is dot. Which x? Oh, sorry. Yeah, r. Okay. So what is the derivative of f? Well, f is scalar valued, so it has one row, and the row consists of its partial derivatives. So I'm going to work in symbols, and then I'm going to plug the bits in, right? So df is going to be df dx. df dy, and dr is going to be a matrix consisting of, R has two components, right? It has an R1 and an R2. So what I need to do here is the partial derivative of this with respect to r and the partial derivative of this with respect to theta in the first row. So we can think about it as a dr1 dr, dr1 d theta, dr2 dr, dr2 d theta. And before you go on, you can actually check to see if you've set this up correctly by making sure that this matrix is a coherent multiplication. This matrix is 1 by 2. This matrix is 2 by 2. So at least I know I can multiply correctly, which is evidence at least that I've got the derivative set up correctly. Is this driving towards the question that we had here? Okay, so let's actually write down the concrete result in this case. And hopefully we're at the point where I can compute partial derivatives relatively quickly. The partial with respect to x of this thing is y. The partial with respect to y is x. And then I multiply that by a matrix that looks like cosine theta minus r times the sine of theta, r cosine theta. And for the purposes of what we've done in here, we stopped at this point, right? We never went any further than this. Now, I could ask you to write down concretely at a given point, like a derivative. So I might say, okay, so this right here, this is df composed with r, thought of as a function of r and theta. So suppose I tell you, what's the derivative? What if I'm at the point radius 1, theta 0? Maybe r. What if I say r theta is equal to 1, 0? Now what? How do I compute the actual numbers? Well, if I have an r theta value to plug in to evaluate this thing at, the r and theta can be plugged directly up into this matrix. That's easy because it's in terms of r and theta. So that would give you, here, I hope you guys remember your basic trigonometry. I miss this sometimes, but cosine of 0 is 1, and then sine of 0 is 0, and the sine of 0 is 0. Oh man, did I make this the identity matrix? That's not very complicated. And r is 1 and theta is 0. So 1 times 1 is 1. Sometimes I write math like test questions like this because they're easy to grade. Now the problem is, where am I going to get the y and the x to be this matrix? Because I didn't give you a y and x. I gave you an r and a theta. But look, I could plug those in here. Right? These are the values that are going to be the x and the y value that I need to plug into this matrix over here to be x and y. So remember, we're thinking of x as being equal to r cosine theta, and y is r sine theta. And so x of 1, 0 is equal to 1, y of 1, 0 is equal to 0. And so what you end up with is the incredibly difficult computation 0, 1 times an identity matrix. It looks like that. All right, so this right here, if you don't want to go any further than that, if I don't tell you multiply all the matrix all the way up, that is the derivative. This object right here is df composed of r evaluated at the point 1, 0. To go one step further, if I say compute the linear approximation to this function at that point, or like at the point 1, 0, that's where you would say, okay, what is the equation for a tangent plane for this thing? Well, the one I'm going to put in my head is nothing. I mean, I can use the gradient one, it's fine. But But it's actually just easier to remember one thing, which is the matrix form of this. And the matrix form says, oh, the linear approximation in variables r and theta is going to be equal to f evaluated at the point 1, 0. It's pretty easy because it's 0 in this case. I guess it's not. It's, remember, I guess we should say f composed with r evaluated at 1, 0 plus df composed with r evaluated at the point 1, 0 times this thing, x minus a. What is this equal to? Because this has this, I mean, this has some, I have to have, I mean, this a thing right here, this vector is the vector where I've been evaluating this thing, right? It is the point 1, 0. So I can think about this as either the point 1, 0, and these as being the x and y components, or the r and theta components of the tangent plane, or I can think about this as a matrix. Since this matrix multiplication has to make sense, I can think about this as r minus r naught theta minus theta naught as a column vector. Right? However you do it, however you decide to organize this, you just need to make sure that the dimensions of this thing line up so that it turns back into a reasonable multiplication when you're finished with it. Right? This is just the equation of a tangent line. The value of the function plus the derivative times some term that tells you how to move away from the point where you approximated. The point where you approximated in this case was radius 1, angle 0. This is the term that tells you how to move away from that point. This is how the slope is set up. And so I guess in practice, what you would say here is this is 0 plus, I'm embarrassing myself. I just imagine you have an identity matrix right here times this vector. That's the linear approximation. You don't go, that's it. You can take it further if you want. I mean, again, admittedly, it's hard to go home at the end of the day and look at yourself in a mirror if you left something times an identity matrix and didn't actually do it. But I guess I told you you didn't need to do any arithmetic. So if you don't feel like multiplying by 1, that's totally fine. I might write something on your exam, like a frowny face or something like, oh man, you multiplied by 1 and didn't do it. But anyway, if you did finish multiplying this out, what you get would be 0 plus 0, 1 times r minus 1 theta. And basically what it tells you is that if you actually do this multiplication, you end up with theta. So the linear approximation to this curve at the point 1, 0 is theta. That just means it's flat. It's not a very interesting plane because they didn't choose a very interesting example to start with. Yep.
Sorry, what's that f times r 1, 0, y?
F times, oh wait, what are you talking about?
The first.
This?
No, the left.
Oh, this is just the value of the function. F composed with r at 1, 0. I actually need to have a starting point, right? I know the height of this function if I knew an x and a y value, right? So I need an x and a y to plug in. So if I have r is equal to 1 and theta is equal to 0, that corresponds to x being 1 and y being equal to 0. So I took 1, 0 and plugged it in. That tells me the height of the tangent plane. So this is just the value of the function.
How that come out to 0?
Well, what's 1 times 0?
So f composed r is 1 of 1 and 0 is 1 times 0.
F composed with r. This is the function xy, right? That's f. So what does r spit out? Remember, the function r is this function. What does r give you if you put in r is equal to 1 and theta is equal to 0? It gives you a 1 in this slot and a 0 in that one. So take the 1 and put it into the x and the 0 and put it into the y. So f composed with r of 1, 0 is 0. All right? Yep.
Is it possible for you to do R compose F?
That's a good question. So yes, actually. Well, no, so the problem is, okay, so the answer is no. And the reason is, what does F spit out as its outputs? This is a great question. How many objects does F spit out? What dimension is F's output? It's dimension 1, right? How many dimensions does R, how many inputs does R need to do evaluations? It needs 2 inputs to do evaluations. So the composition doesn't make sense in the reverse order because F is producing R1 values, but R requires R2 values to work. This works in this direction because R takes in 2 inputs and spits out two inputs. F takes in 2 inputs and spits out 1. That makes sense. Because you're going R2 gets fed into R2 by the function R, and then F can take that and spit out one single value from it. But if you reverse this, you'd end up with, you do F first, and then R requires inputs in R2. So there's no way to bridge this gap right here.
Okay.
The composition is in the wrong order. Yep.
What did you mean by opposite of 7A?
7A. Explain why the directional derivative of F at a point in the direction A is minimized when B points opposite. Okay, so what I mean is there's a little bit of ambiguity in the language about what we mean by parallel versus pointing in the same direction and pointing in the opposite direction. So the point of that question is, we know that D, U, F, and A is equal to U plot the gradient of A, right? And that we also know that this is equal to the magnitude of the gradient of FA times the cosine of the angle between U and the gradient, right? Okay, so what we're saying is, if you're at some point on this curve, which is F of A, and you compute the gradient, so you're pointing this direction, the directional derivative, when it points in the same direction, so U is a unit vector, pointing in the same direction as the gradient, that's when the directional derivative is maximized and its value is this. How do I get the opposite value? What do I mean? Well, turn the directional derivative around and point it this way. What if U points down here? What's the theta between the gradient vector and this direction? Pi, which gets you the negative. That's what I mean by, so when I say opposite, I mean, this is the U pointing in the same direction as the gradient. I literally mean pointing 180 degrees. I sound like I was going to say degrees. I'm sorry. Pointing in pi radians away from.
When you say what is the value?
It's the the reason is, so the magnitude of the maximum is the length of the gradient vector, and the slope in the change of greatest decrease is the negative of that, because this spits out a -1 in that direction. So the length of the directional derivative in this direction is the magnitude of the gradient vector, and in this direction is minus the magnitude of the gradient vector. Because here theta was equal to 0, and here theta was equal to pi. This is like basically the only conceptual question that we spent any time talking about here, was about this sort of geometry. Not like I'm trying to hint at anything by talking about it in here, putting it on the review or anything like that, but you know.
I have another question.
Sure.
I forgot how we showed that.
That's okay, beautiful. Okay, so all you need to do to show that a limit doesn't exist is that you can find 2 directions that don't agree when they come in. So I'm gonna write down an example of how this works with reference to this example. You have f of xy is equal to x squared plus xy minus 2y squared over xy with if xy is not equal to 0, 0. So what I'm going to do is I'm going to compute a limit that restricted to 2 lines. I'm going to restrict myself to the x-axis, and I'm going to restrict myself to the y-axis. So what does this function look like? If we restrict to the x-axis, what are the coordinates of points on the x-axis look like? X, 0. Right? If I'm on the x-axis, I have an x coordinate but no y coordinate, right? So the typical approach to this question is to check and see what happens if you take the limit as x goes to 0 of this function if you restricted it to the x-axis. So if you took this function and you restricted it to the x-axis, it's supposed to be an xy in the bottom?
Yes.
Oh, it's supposed to be.
That's what I'm asking, is it supposed to be? Right. I guess, so the idea here, this one is going to be harder. Let's look at a different line. Okay, now why am I going to immediately say never mind, because I don't want to divide by 0, right? So pick a different line. You can pick any line you want.
I was trying to think like y-axis.
Yeah, that's going to have the same problem, right? So
X equals 1.
yeah, perfect. Right, so let's check x equals y and let's check 2x is equal to y and see what happens. Right, because this is one line coming into the origin and this is a different line coming into the origin, then I've avoided the problem of dividing by 0 by doing this, right? Okay, so that means if x is equal to y, we're looking at the function f of x. The x value is x and also the y value is x because y is equal to x. You do that restriction and you end up with x squared plus x squared minus 2x squared over x squared, which is 0. Well, I've restricted, I'm looking at just cases where the x and the y values are the same. So I've replaced y with x squared. So everywhere I saw a y, I put an x into the formula.
Okay, so where's that? But then you plug it back into the.
Yeah, you start with the function, you just put the new variables into it. You get 0 if you do it here. Now, if this problem is set up to be easy, if you do this, you don't have that happen. Right? If on the other, so what is the limit as x goes to 0 of that function? 0, right? The limit of 0 is nothing. The limit as x goes to 0 of f of x, 0. The function was 0. If instead you look at f of x, 2x, you get x squared plus 2x squared minus, let's see, 2, there's a 4, so minus 8x squared over 2x squared. Well, all the x squareds cancel out of the problem, right? All the x squareds are gone because you get 3x squared minus 8, so it's minus 5x squared on the top and 2x squared on the bottom. So this is minus 5 halves. So on this line, when y is equal to 2x, now the function is constantly equal to minus 5 halves. What's the limit as x goes to 0 of that? Well, minus 5 halves. Since the limit on two different lines is different, the limit cannot exist. The idea that we've done here is we said we've got f, we checked this line and we came into the origin, and every point on here looks like xx. And we check this line and we come into the origin where every point looks like x2x. And in both cases, we get different algebraic simplifications. So the limits are different. And if the limits in two different directions agree, then it fails. Yep.
Wait, we're checking if f of xy has a limit.
You're trying to check if this function, so that you're trying to disprove. The harder version of this question is to say prove or disprove this function has a limit. That's a me question, right? I'm just going to tell you that function doesn't have a limit. So if I tell you that doesn't have a limit, you can prove it by finding two different lines to approach the origin on. Like if you can find two different lines to approach the origin on, then make the function turn into two different values, then you're just done. Limits don't agree on these individual lines, so there must not be a limit at that point.
There's no limit.
There's no limit. The fact that these numbers are different means there cannot be a limit. Now, if you guys remember the image, the display that I put up there earlier, we also have I'm gonna ask you a harder question, which is if there's a limit on every line approaching the origin for some function f of x, every single line through the origin has a limit, and that limit is the same, does the function have a limit there? And the answer was no, right? We had that crazy example where if you came in on lines, it all went through 0, but if you came out on parabolas, the parabolas had different heights depending on how the parabolas came in. So don't get it in your heads that this means that, oh, I checked it on lines, so the limit must exist. I'm not going to ask that question, but it may show up in the future. Good question. That was question 3. Question 3b. I say, consider some function that has some gnarly, like division by 0 in the bottom, right? And I say, is it continuous at 0, 0? And so how do you show that?
Or if they're the same, then.
Well, this one, yeah, you can literally just factor, right? So if I ask you to show that a limit exists, you know I'm not going to make you do an epsilon delta proof. I mean, I could, but that's what we mean, right? So if I give you one of these exercises and I say, hey, show that this function is continuous or is it not continuous, I'll be more concrete about it. If you get a function that looks like f of xy is equal to, and you should be really suspicious if you start looking at things that look like squared things that have been subtracted from each other. This is probably like tattooed in your brains forever. If things are subtracted and they are perfect squares, it might very well be the case that you could fruitfully rearrange this as a difference of squares.
Y. Y.
Yeah, this was a y. Oh, look. They cancel. So as long as you stay away from 0, 0, this function is actually equal to x squared plus 2y. Is that function continuous at 0? Why? The polynomial. What's the limit of that function as xy goes to 0? 0, because it's polynomial, right? So is this function continuous at 0? As long as I plug the hole correctly by making the value 0 at 0, which I believe I did, right? Yeah, this is continuous function. So the argument here is this looks bad because you're dividing by 0 and you've got a 0 in the numerator, and 0 over 0, you can't use any sort of L'Hopital's rules ideas here. But if I write up the problem in a trick way so that algebra makes it fall into a polynomial, then you know it has to be continuous. Yep.
Also, these two lines you take are random lines.
They're random. The only reason I didn't pick the line where x was equal to 0 is I didn't want to divide by 0. I could have picked any lines I picked here, y equals x, y equals 2x, y equals 3x, y equals 10x. I'm going to get different values for each one of those. Even if you put in y equals minus x, you get a different.
But it's just because they're both approaching the origin, so it's anything that's approaching the origin.
Basically, to make the problem tractable so I could use one variable theory on it, I'm turning a function of two variables into a function of just one variable, and then showing that as a function of one variable, it doesn't have limits that agree. This is the same thing as showing that a function does this. Come in from one side, it's one limit. Come in some, this is a classical case where limits don't exist, right? What else? Yep.
Well, just like hypothetically, if like the limit of a line approach to the point didn't match with like a parabolic approach to it, would that mean anything?
Yeah, it would mean it doesn't have a limit, right?
So,
So
you
like,
compare like different like origins.
yeah, and this is why the when you're actually using these things in practice, you actually have to consider not just, it's like you actually think about it spheres around the point that you're studying. And the sphere has to get smaller. The function, as any sphere gets smaller and smaller, the function has to look like it stitches together there. So the whole ball has to have a limit that approaches in, which means you almost have to do it with epsilons and deltas, because picking any line isn't going to be good enough. What else?
Professor?
Yep.
So the idea of partial derivative being continuous, that's to show that the function is differentiable, right?
Yes, actually, that's a good question. What is the definition of, for us, what do we mean by, what does this mean? If I say f is C1. Almost, no, once, it's more than once differentiable. So f is C1 means f is once, I'm gonna leave a blank here, there's a word missing, differentiable. What needs to go here to say something is C1? Continuously differentiable. It's not enough that f has partial derivatives that are defined everywhere, which is what we mean by differentiable. If we want nice functions, we require C1 function means f is once continuously differentiable. Okay. So C1 functions are continuous. And actually, I don't know, do you guys have a quick example in your head of a function that's differentiable but not continuously differentiable? Okay. Okay, if you plot this function turns out not to be continuous. This is the one you put in your calculator and you zoom in forever. It's the same shape over and over and over again that high school teachers love making their students do. You can actually control the behavior of this function by multiplying it by x. So if you took this function, which looks like this, and you multiply it by x, well, if you stick the x in front, then you get this function. So there's lines that look like this, it's y equals x and y equals minus x, and the function comes in and it gets infinite, but it piles into 0 while it does it. So this is a continuous function, but if you compute its derivative, it's not differentiable. If you put an x squared in front of it, Now you've got a function that's not controlled by lines, but it's controlled by parabolas instead. So this goes to 0 even faster because it's being crushed by a parabola above and below it. And the fact that you put this parabola in there will end up showing you that this function turns out to be differentiable, but the derivative isn't continuous. If you put x cubed in there, it's once continuously differentiable, but the second derivative exists everywhere, but not continuously. So this is you might think about trying to learn this. These are called the topologist sine curves. They're really awesome examples of ways of introducing prescribed levels of x. Right. So if I put a 2 up here, I get a once continuously differentiable, but not second continuously differentiable function. If I put a 3, I get twice continuous differentiable, but not 3 times. These are the best things in math are the worst things. And this is one of the worst things. What else? What else? Oh, let's talk about this one real quick. Since I'm going to give people an opportunity to raise their hand here, but I got a point that I want to make. All right, somebody had their hand up. Yep.
I just wanted to say quick over 7D.
7D.
Just like how to go about it.
Yeah, so the thing about 7D is that we picked up this theorem at the end that said how to compute there was a theorem that said how to calculate a tangent plane for an implicitly defined surface, right? So in 7D, the theorem that you were using was,
You already put everything on one side.
yeah, exactly, that you have x squared plus y squared. In this case is plus 4y squared minus z squared is equal to 0. And then you think about this as f of x, y, and z. And then this is the object that you use to take the derivative and compute the tangent plane. Right. So this was the implicitly defined surfaces. But the idea here is that you can still write down a linear approximation in terms of this implicitly defined thing. What am I doing in this question? I'm going to ask you, I'm going to give you a baby version of this. Let's let f of x and y be equal to x, y to the 13th. I'm going to ask you to compute a partial derivative for me. What is d10 of dy, 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 dx, dy, dy, yeah, 1, 2, 3, 4, 5, 6, 7, 8, dy. Why is it 0? You can put the derivatives in any order you want, right? This is a polynomial. It's infinitely differentiable. The idea is that means mixed partials of the same order are equal to each other, no matter what order you do the derivatives in. Do I really expect you to do 10 derivatives here? Or are you supposed to observe, look, x is to the first power, and I've asked you to compute 2 derivatives of x, right? So the idea here, this is a way of quickly checking if you guys remember that mixed partials are equal to each other if the functions are nice. This is a nice function. You can compute the mixed partial in any order you want. So the way you should do it is d10, stick your 8 derivatives of y last and put your 2 derivatives of x first, and then you're just going to get 0 out because the second derivative with respect to x of this is nothing. Okay. You should be suspicious if you see a problem that looks ridiculous. I just saw it in the book and I thought it was cute. So it's a cute problem. And since almost everybody's here, it seems like a shame to waste a question like that. Anything else? Oh, as far as the other thing about the cone question, so I should address this. The second thing says, what happens if you try to find an equation for the tangent plane to S at the origin, and why does that happen? So I'm going to draw, even if you got no idea what's going on mathematically, I'm going to draw a picture of a cone, and you guys can tell me why it fails if I try to draw a tangent plane. Because you should suspect, just on the basis of a picture, something is going to go wrong. Now, like every good math student, of course, we write cones as 2-sided cones because it's a 2-sided cone. I guess maybe it's not in this case. Just imagine, like, what goes wrong here? What goes wrong at that point if I try to draw a tangent plane?
2.2.
The derivative actually is not defined, right? It's part of it. Like the derivative here, but why is the derivative not? What? So this function is actually not differential here, but why? Like let's make this clear and just do this with it. Yep. It's a sharp turn. How can, what if you were trying to explain this to somebody in terms of tangent planes? You do need 3 points to define a tangent plane. What does it look like the tangent plane, the direction of the tangent plane should be if you approach that point from this side, right? All these tangent planes along this line point the same way, right? This thing has gradient vectors or normal vectors sticking at it like this, and then you get here, and all of a sudden, we go, oh, okay, that must be what the direction of the tangent plane is. It points this way. On the other side, as you slide closer and closer to that point, as the derivatives are defined and defined and defined, everything's okay, except now it looks like your limit for the direction of the tangent plane should be this. The fact that you have 2 independent directions that should be your tangent plane makes the derivative, it basically means it's not derivative or differentiable there. And if you try to compute a normal vector with a cross product, the cross product will fail. You get 0 out of the cross product. Right? Yeah, sharp points. Favorite sharp cusps. They're better. Terrible things. Anyway, okay, so if you haven't done it yet, I would work through these exercises. I'll post solutions tomorrow. Do not do 6C unless you just are bored and want to calculate differential operators because you got nothing better to do. If you have questions about how any of these ideas connect on, I will do that. Next week, we'll pick back up. I haven't posted new homework yet because I want you to get through the exam first. If I do post the homework, the due date will not be until a week after we start, after the exam, right? So we'll just get back, I'll post a week's worth of homework. We'll have that due, whatever, 5 or 7 days after that.